on applications.
Good afternoon. Welcome to the NSC Center for Behavioral Sciences seminar series. The NSC CBS was established in March 2020. Over the years, the center has become a focal point of research synergies in the domain of behavioral science and its application to management studies. Today, the NSC CBS is pleased to host Professor Sudipta Sarangi, Professor and Department Head of the Department of Economics at Virginia Tech. Previously, Professor Sarangi served as a distinguished professor of business administration at the Louisiana State University and a program director at the National Science Foundation. During the 2023-24 academic year, he was a fellow at the Collegium de Lyon, part of the French Institutes for Advanced Study. Professor Sarangi's research spans a diverse array of fields, including network theory, experimental and behavioral economics, and development economics. He has consulted for prestigious organizations such as the World Bank and FAO. In addition to his extensive publication record in various academic journals, Professor Sarangi serves on the editorial boards of several notable journals, including the Journal of Economic Behavior and Organization, the Journal of Public Economic Theory, Oxford Open Economics, and Economic Modeling. Beyond his academic publications, Professor Sarangi has authored The Economics of Small Things, a book aimed at non-economists that elucidates economic concepts through everyday phenomena. Thank you, Professor Sarangi, for having accepted our invitation to speak at IIM Ahmedabad. I would like to invite Professor Pritha Dev to open the seminar by presenting a token of our appreciation to Professor Sarangi, followed up by an introduction to the talk.
Thank you, Pritha. Yeah. Thank you.
Thank you. I think Sudipta will take over from here. We'll take questions as and when they come along. And I know this is a diverse group. Sudipta's talk will be technical, but he promised that he's going to introduce a classic paper first before he goes on to his own work. So we'll get a fair grounding into the literature as well. Thank you, Sudipta. All yours.
Well, thank you, Varuna. She has made my trip extremely easy, having taken care of everything. Of course, Pritha and I go back a long way. So thank you, Pritha, for inviting me. I know Tarun as well, and India. It was good to meet Jivant this time, several of the PhD students. Thank you for having me. I'm glad to be here. My brother actually lives in Ahmedabad, so I do have occasion to visit the city. But depending on the number of days I'm staying here, I let people know whether I'm in town or not. So this time I was here for about 4.5 days. So I told people I'm here. Last year I was there for 2 days. I didn't tell anybody I was here. All right, so I'm going to talk about games under network uncertainty. This is joint work with Promit Chaudhary, who is a PhD student at Virginia Tech, and Hector Zavelas, who's also my colleague at Virginia Tech. Matt Jackson is at Stanford. And I am going to talk about incomplete information games in networks. Feel free to stop me as we go along if you have questions. I would rather you ask me questions as we go along than wait till the end. Yeah, that said, let's move along. So first, let's say, what's a network, right? You can think of a network as anything that defines how the agents interact with each other. So it's one way of defining the interaction structure between agents. That's what a network gives us, okay? The networks literature in economics can be divided broadly into 2 types of strands. One is about network formation. So how do networks arise in the first place, which is one of the ways in which the econ literature differs from the literature in sociology, physics, math, and so on. That is, how do these networks emerge? What incentives drive the emergence of networks? What is their architecture? And things like that. The second strand of literature in econ takes the network as given, but there is an economic activity that's happening on the given network, right? So it could be exchange of information, it could be exchange of favors, it could be insurance, it could be altruism, it could be playing prisoner's dilemma, whatever. So if you think about prisoner's dilemma, of course, you're going back to the local interaction literature from the 1990s. Yes, go on.
those are branches of science that are representation of reality, one part of reality, and another.
Very good. So to go back, to answer that question, I'll go back to the roots, because you could say, why do we have different social sciences? They're all studying human behavior. So why do we have sociology and economics in the first place? But we do have them. The reason we have them is because the methodology is different. Okay, so economists are looking at incentives. They're looking at strategic behavior. Sociologists are mostly taking the network structure as given, and they're doing what is called social network analysis. They're looking at structural properties of the network rather than asking questions like, why did this network emerge in the first place? Okay, so that's one way of thinking about what's the difference. But I don't think I'm adequately informed to answer that side. I can answer the econ side. Okay. Right. So, typical paper assumes that we know the network. Right? The common knowledge of the network architecture is something we always assume, but in practice, agents rarely know the architecture of the network. Okay, the entire architecture of the network. You will have partial information of the network architecture. You might know your friends, and you might know your friends' friends. Some people might know friends' friends' friends. Some other people may just know friends, and so on. Right? So this is one of the things we want to think about. So this is going to be the starting point, that agents rarely know the full architecture of the network. So the type of questions we want to answer is that, and these are interrelated questions, right? So how will behavior change if you have local information? How is this different from behavior under complete information? And things like that. So this is roughly the question I'm going to tackle. And therefore, as Pritha mentioned, I'm first going to explain the complete information model to you. Okay. Once I explain the complete information model to you, then only I will talk about the incomplete information and what happens under incomplete information. Okay. I will skip over the literature. I'll not go into details of the literature, because if people are not familiar with the literature anyway, there's no point me spending a lot of time on the literature, right? So I'll give you a very brief idea. So these are papers that look at games played on networks. This one I will talk about in great detail later. This is public goods. This is a type of public goods problems. Unknown network architecture. Breza Chandrasekhar Taba Salehi. They look at the data on Indian villages, sure. One of the things we cite this paper is that it turns out people are not very good at predicting their friends' friends. Okay, so we know our friends, but we're already very bad at knowing who our friends' friends are. Okay, this is borne out by the data, that Arun's data on the 70 Indian villages. Krishna Dashrath has this paper where he argues that people know the degree distribution, and then he looks at limiting properties of the degree distribution in terms of what happens when the network architecture is unknown. Yes, Jim, you had a question. It is a Harsani model that we're going to introduce. So we are going to introduce, that's exactly what we're doing. Okay. It's not an easy problem. That's what we think. Okay. I mean, most of the earlier literature has worked with degree distributions. And the problem with degree distributions is you can't study strategic behavior. Degree distributions will basically take results from random networks and give you Erdos-Renyi type results or limiting distributions and things like that. But the Harsani type framework does not exist. This, I think, at least as far as we know, this is the first paper to do. There is a paper that does incomplete information, and I will tell you in a minute. So this is the Dimarti-Zenu paper. This does incomplete information on the parameters of the game being played in the network, not incomplete information on the network, right? So if you're playing whatever, if let's imagine you're playing Prisoner's Dilemma, then this is like saying, okay, I have uncertainty about the parameters of the Prisoner's Dilemma payoffs. Okay, so Gagliotti et al. Does the degree distribution stuff on the network. So you know your degree distribution. You have an idea of everybody's degree distribution, but you don't know who they are connected to, which is a very unsatisfying assumption. And in a sense, you're saying that, okay, I know how many degrees people have, but I have no idea who they're connected to. In fact, I need the assumption that people don't know who they are connected to. Okay, so they need that anonymity assumption. Okay, Golub and Morris, like all Steve Morris papers, is about higher order beliefs. So I will not go there. So this is roughly what's going on in the literature. I'm not going to spend more time. Okay, so how do I represent a network? A network can be represented by a picture, of course, which connects the different people, and you will see examples of that later. But I can also represent it by an adjacency matrix. So this is my adjacency matrix representation. If there is a link between two agents, then it is denoted by 1 in the adjacency matrix. If there is no link between two agents, it's denoted by a 0 in the adjacency matrix. And I will show you an example of an adjacency matrix and a picture later on. Okay, so we'll do everything from scratch. I'm going to define what is a neighborhood. Your neighborhood is the friends you have on Facebook. Okay, and the cardinality of that neighborhood is your degree. So this is the number of friends you have on Facebook, right? So this is your degree. This is how many people you're linked to, the count. And the neighborhood is that set that tells you who all are in that set. Yes. I don't have degree distribution in this paper, so let's not worry about degree distribution. Okay, degree distribution would basically tell you what is, I would draw from a distribution, I would draw something and they would tell me how many people.
Decide on the distribution on the basis of that, like
the network is drawn from an arbitrary degree probability distribution. The degree distribution is drawn from an arbitrary probability distribution. Okay, but let's not get there. Yeah.
So this doesn't distinguish between follow and follow back. So
Directed and undirected links.
yeah.
So this, okay, I'm going to work on a undirected, unweighted network. If there were weights, then the intensity of the link would be captured. So it wouldn't be 0, 1. It would be the complete, the interval 0, 1, closed interval 0. But this is binary, 0 and 1. So it's unweighted. And then I also have undirected. So undirected means two-way street. So if I'm connected to you, you are connected to me. Directed would be one-way streets. The framework we have allows you to deal with directed networks, but I don't do that. Okay. All right. Agents are all members of a network. So this is Ballester et al. Econometrica 2006. So let's start with this utility function. Let me first explain what happens in this utility function, and then we will see what's going on. Okay. So G is the network. A is your effort choice. Okay. So if I look at this part, let's just look at the first two terms. What are the first two terms telling me? It's basically giving me concavity in effort, right? It's like the standard principal agent model. My payoff increases with my effort, but at a decreasing rate, right? So the first order condition there would give me something linear. Okay. So that's very clear, right? So then this part is the payoff from the network. Okay. So this part tells me that my effort is AI. Okay. Lambda is a parameter that we will take as positive for now. And it's a small number. Lambda is a small positive parameter. I'll talk about what it means if lambda is negative. Okay. Gij's, remember, our matrix has entries 0 or 1. If two people are connected, Gij takes the value 1. If they're not connected, it takes the value 0. So Gij basically an indicator function, right? And then I multiply that by the other person's effort. So if I'm considering a link between I and J, then my payoff depends on my effort and the other person's effort. And I will, of course, sum this over all possible links that I could have. So that's what the summation sign is doing here. Okay. Now, if Gij is equal to 0, then for that particular pair Ij, this term will take a value 0. Okay. If Gij is equal to 1, then it will be lambda times Ai times Aj. Very clear? I sum up over everybody. So what is lambda positive mean? Lambda positive means we have strategic complementarity. If Aj increases, then Ai will increase. So if my project partner is willing to work harder, then I am willing to work harder as well. That's the idea, right? So if you're working on a team, if the other person in your team is willing to work harder, you are also willing to work harder because your payoffs go off. go up, lambda is positive. If lambda was negative, then we would have strategic substitutes, which is most oligopoly games, right? So your profit decreases when the other firm's output increases. Strategic substitutability or strategic complementarity is the cross partial derivative of the profit function, right? So d square del square pi I, del I, del j. Okay, that's what will get me strategic complementarity or strategic substitutability. Okay, and effort, of course, belongs to, it should be R plus, actually, negative effort. It could be 0. Actually, it could be 0. It could be R. All right. So this is called the linear quadratic payoff function. We like this payoff function. Why? Because it captures the network effect nicely, along with my own effort. Lambda being small ensures that the network effect does not outweigh my own effort. So primarily, my payoff should come from here, and then some payoffs from the network. When I take the first order condition, I will get a linear function. The best response for such a function is linear. So when I want to solve for the Nash equilibrium of this game, I will get a system of linear equations, which we love because we can solve that. Right? So this is the Ballester-Calvert-Mengolzano Econometrica 2006 payoff function. So let's look at the equilibrium in this game. All right. This is the first order condition. Okay? If I take the derivative, this is what I will get. If I rearrange the derivative in matrix terms, well, actually, before I do that, okay. So if I rearrange this, then I will get this expression I minus lambda g, okay, to the inverse. Okay.
This is a classic paper you talk.
Yeah.
So is this that functional form of the AI multiplied to the summation? So lambda into AI multiplied to the summation. So that's a particular specific form, right? So
The linear quadratic form.
yeah. So just the last term, the fact that like you to benefit more from your network, you need to also put in effort. Has that been generalized to other?
I mean, so for you,
So that's a very particular relationship, right? That I have to work in order to benefit from my network. I mean, ideally, I would just rely on my colleagues and free ride on our papers with them.
So that's strategic substitutes, no?
Right. So for that, how would we capture that?
Lambda negative.
So
So if if the other guy is working harder, then you work less.
Right.
You free ride, right?
Okay, I see.
So if you belong to Bertie Wooster and his friends, then your friends work harder, then you can be the socialite Bertie Wooster and do no work. Right? So that's the lambda negative will capture that. Very good question. It's very difficult to introduce heterogeneity for every different participant. Sure. So you can take this as the lower bound or the upper bound, then the results will work accordingly. But this is a theory model. So let me just explain to you what the best response matrix looks like. And then if I were to introduce AI into the best response matrix, you will go crazy. You will not be able to do anything, right? So this is AI, okay? Now, if AI is different for all links, then I have to, for each player, I have to have n minus 1 best responses. And then I have n players. So I have n minus 1 into n best responses. And then I have to solve that system of equations to get the answer, okay? Lambda, you can vary lambda, it doesn't matter. It's a scale parameter. So so I will talk to you about lambda and what are the limitations on lambda when we go further into the problem. So I'll explain to you. So one thing we have to remember is lambda cannot be very high. If lambda is very high, then your own effort really doesn't matter. The network is generating so many benefits or so much benefit in terms of benefits that the network drives everything. We don't want that. So lambda has to be small. Okay. So we'll talk about what determines the value of lambda. Okay. And once it is within that bound, then I can vary lambda. Essentially, what I need is convergence. Okay. So let me talk about the idea of an influence matrix. As I said, if I rewrite this first order condition, then the optimal effort will look like something like this, okay, which basically, if I have 1 plus r square plus r cube and so on, then that geometric series when r is less than 1 is 1 over 1 minus r, right? So this is the term. Okay, so I will get, this is called the influence matrix. What is the influence matrix? The influence matrix is telling me the paths of different, take an agent I, all the paths of different lengths, all the walks of different lengths from that agent to every other agent in the network. I sum up all these walks, okay? So, for example, G gives me walks of length 1. G square gives me walks of length 2. G cube will give me walks of length 3, and I pick any particular element of G3. Okay, so if I pick G12, okay, in G square, okay, that tells me all the paths of length 2 between 1 and 2. Okay, so this is what these matrices will give. So I can write down the influence matrix as this. The longer walks are discounted more. So what determines lambda? I need this thing to converge, otherwise it explodes, which means that lambda, so technical condition de Bruchstein 1953, lambda has to be smaller than 1 over the largest eigenvalue of this matrix. Alternatively, the easy way to think about it, the largest benefit I can get from a network is n minus 1. If everybody gives me benefit 1, there are n minus 1 other people. I connect to everybody n minus 1. Therefore, if lambda is less than 1 over n minus 1, within that, any variation of lambda is all right. Okay? So I can heterogenize lambda as long as it does not exceed 1 over n minus 1, then this series will not explode and I'm fine. Okay. When I multiply this by a vector of 1s, then I get a number for each of the n agents, and that's called that agent's Bonacid centrality. That's a measure of how many paths of different lengths go from agent I to all the other agents. The one with more paths has a higher Bonacid centrality. Of course, longer paths are discounted more. Yes, go on. The last point. Katz's Bonacid centrality is a measure of centrality or an importance of an agent in the network, which says that from agent I take all the paths of different walks, all the walks of different lengths to every other agent in the network. I sum them up. Longer walks being discounted more. Lambda is the discount factor, right? And that gives me that particular agent's Katz's Bonacid centrality. Okay. The higher the sum, the higher is the Katz's Bonacid centrality. So the Katz's Bonacid centrality is basically you take the influence matrix, multiply it by a unit vector of 1s, and you will get the Katz's Bonacid centrality.
Yeah, hello. So one clarification about G to the K. Essentially, that's the graph matrix. You're multiplying it over K. So you'd get for each node ij, you'd get the number of paths from I to j. Is that right?
Sorry, repeat again.
Say, for example, you have n, what do you call it, n cross n matrix G, and any particular node Gij in this G to the K would be the number of.
No, Gij is not a node.
I know. I mean,
Gij is the pair. I to j. So G will give me walks of length 1. The number of I and j. The number of walks of length 1 between I and j. G square will give me the number of walks of length 2 between I and j. G3 between, and so on, right? So Gk is the number of walks of length k between I and j, and the longer walks are discounted more. Okay. This infinite series will. Yeah, that's kind of right. What am I doing? Oh, I need to go back. Yeah, so this infinite series will not converge, no? All right. So what is the Nash equilibrium effort level in the game? The Nash equilibrium effort level in this game turns out to be proportional to Bonacid centrality. So the key so the first result, theorem 1, Ballester-Calver-Mengol-Zeno, is the Nash equilibrium exists as long as lambda is less than the largest 1 over the largest eigenvalue. Theorem 2, the Nash equilibrium is proportional to Bonacid centrality. This is a beautiful result. Why is this a beautiful result? Because if you buy into the fact that the utility function satisfies linear quadratic form, I don't care about its parameters, then I don't need to know anything about the utility function. I just give me the graph, I will compute the Katz-Monachit centrality, and I will say that's it. That's the optimal effort level. Okay? So I don't need to know anything else about the agent behavior. You just give me the network. Okay? So that's why it's a very nice result. I mean, they have a third result, which is identifying key players. So I will not go into the third result. It's about how to define. Yeah.
So normally when you have a graph, it's like limited in size. What we're doing is we're taking an infinite series. So you're basically adding cycles and loops, but you're just discounting them as well, right?
No. So
It's a finite size graph. Can I?
yeah, please go ahead.
It's a finite size graph. Let's say it's a graph between all the. The point is you are connected to something. If you are connected to A, call it I and J, and then E is connected to something. So if you are going from U to N, then it's a length 2. It's on the same graph. Then you can have a length 3, then have a length 4. The network itself is not changing.
That's
The network is N. Fixed.
So that's how I'm saying that your matrix G can explode in the sense that
What do you mean by G can explode?
K can explode as K keeps going there, right? Because the number of paths of length K will keep on increasing.
But I have lambda discounting it sufficiently.
Taking lambda with this constraint is because we don't want it to explode. But
No, but there's also an economic reason for that. The economic reason is that the network should not generate too many benefits. Otherwise, what's the point of my own effort? No, it's not an assumption. I'm saying your heart, see, if all your benefits in your life come from your extended network, then you don't need to put effort, no? So your own effort must give you primary benefits. The network adds on. So your cake is your own effort. Okay, the icing on the cake is coming from the network.
people get in and then they generate a lot more than they could have been.
So they generate a lot more, but that lot more should not overwhelm your own effort, the benefits from your own effort. Okay, I need to get on because it's already halfway. All right. So what happens? What happens in this type of network? Why is it that paths are important? Okay, so let's try to understand this. So suppose agent 5 increases their effort. Okay, now imagine this is a simultaneous move game. So this is just an example, right? It's not happening sequentially. 5 increases their effort. As a result, 3 will increase their effort. When 3 increases their effort, 2 will increase their effort. 1 will increase their effort. 4 will increase their effort. Okay, which is why the strategic complementarity says that if I can keep track of walks, then just keeping track of walks is going to give me the optimal effort. That's the intuition for the result, that the optimal effort level is proportional to the number of walks. That's it. Because one person increases effort, this increases effort, and so on. Okay. All right. There is a lambda. There is a 1 missing here because last time I was presenting, I didn't make the correction. Ehud Kalai pointed this out to me. No, Phil Rennie pointed this out to me. So it should be a unit vector here, right? Otherwise, I have a matrix plus a bunch of vectors. So obviously, it doesn't add up. Anyway, so I pointed this out just in case anybody wants to catch this. All right. So complete information over. Okay. Now we're going to go to incomplete information. So how is the incomplete information model going? Nature picks an undirected, unweighted network from some given arbitrary probability distribution over all possible networks. Okay. Once nature picks a network, players learn their connections. Okay. I'm going to explain the intuition with this model, but the model is generalized to arbitrary type spaces. I'll explain what I mean by arbitrary type spaces later on. So you see your neighbors, but you don't see beyond your neighbors. So you don't see your neighbors' neighbors and their neighbors' neighbors and so on. Okay. So all you see once nature draws a network is your immediate neighbors. Okay. Then you have to update your beliefs about the rest of the network because the optimal effort level, remember, we already saw in the complete information case, depends on the entire network structure because you need to know all these possible walks. Okay. And then agents will simultaneously exert effort to maximize interim payoffs. Okay. So if this is a graph, right, then this is the adjacency matrix that goes with the graph. Okay. What does incomplete information say? Incomplete information says that player 1 knows that they are connected to 1 and 2, to 2 and 3. They have to think whether 2 and 3 are connected or not. Okay. What about player 2? Player 2 knows that they are not connected to 3. So they don't have to form opinions about that. They know that they are connected to player 1. So all player 2 has to do is form beliefs about whether 1 and 3 are connected. Similarly, what does player 3 have to do? Player 3 has to form beliefs about whether 1 and 2 are connected or not, because they already know that they are not connected to 2. Okay. Yeah. So you can work on an extension of that. That becomes sort of an infinite game. We have some progress on that, but it's a very complicated infinite game. Yeah. So remember, this was our initial network. This is simultaneous.
There's an updating of something.
Yeah, you have to update beliefs before you take your optimal actions, right? So let me just define the type space, okay, which is what I'm coming to. So knowing this, yes, yeah, that's the innovation actually. All right. So the innovation is the type space is the row of the adjacency matrix. Your local connections it defines your type space. Once nature draws an arbitrary network, you know your neighbors define your type space. That's it. Okay, because then you have to have beliefs over your neighbors' neighbors. That's it. So that defines your type space. Okay, and the arbitrary type space would be different people have different levels of knowledge of this network. Okay, so it's possible that player 1 knows the first 2 rows, whereas player 2 only knows 1 row. So that would be so the main results hold for that. But I will not go into that because intuition is hard with that. Okay. So
I know the Valescar and one major innovation that I thought they had is that while they build it up for the competition, but the result is basically an equivalence between eigenvector separability and flashability. So there you do not need to know the network structure as long as all the diagonal.
I mean, not eigenvector type. The cat's bonus H. Cat's bonus H. Yeah.
So then is it also a kind of information to environment that one can not make? Well, one can say that I do not know who is connected to whom. There is a social media who says that this is the diagonal. And then all the things will go through, right? So basically my point is it the only way to make this complete information assumption? Or the other possibility could be I can see why this is a very natural exception, but can it also be the case that I'm unsure about the other different states that other than
You can, I mean, if I give you this information, yeah, okay. If I can give you this information, you can compute other players' centrality you can compute their expected centrality, right? But centralities will not work. I have a little bit of there is a remark, there are 2 remarks in the paper which talk about this, because here you have to condition on every player's type. Otherwise, you get different answers. Okay, so I have to condition on every player's type along the path or along the walk that I'm thinking about. So hang on. Okay, hang on, we can talk about that. So what is the type space? Well, the type space is what is my link with everybody else. So 0, 1 to the power n. Okay, GII is always 0 in this literature. Okay, so essentially GTI is my type, which is the identity of my neighbors, right? So this is what I need to have beliefs on. Okay, and G is the type space, which is the Cartesian product of GI. Now we have to rule out certain types of inconsistencies. So suppose player one has this type, okay, and player 2 has this type. This is not consistent. Why? Because this says that 1 is connected to 2 and 1 is connected to 3, whereas this says 2 is not connected to 1, right? Because this is a 0 here. So these types will have to be ruled out because we have explicitly said that we will focus on undirected networks. This would require a directed network. So these types will not be allowed. So they will have zero probability. Okay. So P is the admissible probability distribution, which basically means this type of restriction, and this is common knowledge. Okay, so everybody knows that nature will draw undirected, unweighted graphs. That's common knowledge. All right. Yeah. For things that are inconsistent, the probability of those things is zero. This is what I just said. Now, if my utility function now will have to change, because now for every type of every player, I will have an effort level that will depend on that type, right? So these terms, if you compare with the complete information case, is the same thing, except that I have included the type. Here, I have to, so if the link exists, so that is still there. Given my type is Ti, what is the probability that the other type is Gj? So that probability needs to be taken into account or has to be put in there, and then I condition on that player's effort is conditioned on that. Okay. So the first order condition changes. It needs to take into account all possible types. So summing over all players, here I'm going to take into account all possible types. Okay. All right. Now, my first order condition no longer looks as simple as it was. So there is no M matrix. Now there is a matrix B here. And this B matrix itself is composed of a bunch of matrices. Okay. So this matrix is a matrix of possible types for player 1 and player 2. This is 2 given 1. This is 1 given 2, and so on. Okay. So every player, there are n players. Every player can link to all the other players. Okay. How many possibilities? To the power n minus 1, right? So I can either have a link or not have a link. So that's called gamma. Okay, so that's given by gamma. So then the dimension of this matrix is n gamma times n gamma. Under complete information, this is just one entry in this n gamma times n gamma matrix. Okay. So if I were to take this entry G12, then along the rows, I am running all the possible types of player 1. Okay, all the gamma possible types of player 1, and along the columns, I'm running all the possible types of player 2. And the optimal effort has to be chosen for each of those types, right? This will be, for example. So inconsistent types will have zero probability here. Yeah. Okay.
I have one minute. And then about the second player, I have found it's about this class. Right? And conditional on this participant. Now he can have beliefs only that consistent with this type I first assigned with him. He will do something that optimizes.
No. His beliefs are not conditional on what types I assign to him. Everybody's beliefs have to be conditional on the undirected.
I violate the stuff he's correct.
Yeah.
And then I will do the
Yeah. Absolutely. I don't know his connections. Yeah. Or I know the type, right? But I know his type in the sense that, no, I don't know his type. I know I'm connected to him. So now I'll have to consider all the possibilities that particular type can have. And then I have to consider all possible types of that guy.
A type for 2, then my type for 3, 4, 5, they get limited.
No.
Because if I assume in my type space,
No, I know the type.
my type,
I know my type, so I know who all I'm connected to, right?
the space of possible types you can assign to all the n-1 players, that is also restrictive. Because as soon as I assign a type to, as soon as I pick one of the types for 2, that restricts the choice for 3 plus.
Agreed.
So
Exactly. Yeah, but I have to take all. So when I do the computations, I'll take all possible types of 2 into account. Right? So once I have, if I'm connected to 2, I have to take all the possible types of 2 into account and do the computation over that. Okay? That's right. Okay? So yes, it does restrict, but I have to take all of them into account. Which is why the problem is tractable in some ways. Otherwise, it would be intractable. Okay? So as I said, I'm going to be able to allow for arbitrary type spaces, which means, Tarun knows everything and everybody about the network. Okay, but Jivanti just knows his immediate friends. I think somewhere in between. She knows friends of friends and friends of friends or something like that. Okay, so that's if we allow that, then we will be able to solve the problem as well. So the 2 main results. So we have an example. So we're working on one where we say that he knows everybody, and the fact that he knows everybody is common knowledge. How does that change the problem, right? So that I'm not going to talk about today because we haven't finished working out the proofs. But yes, eventually we're getting there as well. That what if there is one player in the network who knows everybody and who knows the entire network, and everybody knows that this person knows the entire network. All right. So what does this mean? First order connectivity basically means that you know this and you have incomplete information about these things. Second order friends of friends would mean that you already know this and now you only have incomplete information over these links. Right? So if you know your friends, so here player 1 has to have beliefs about these kinds of links. Here, player 1 already knows that. So this is how it changes the network structure. So how many rows of the matrix you know, and that can vary from person to person. Okay. All right. As long as lambda is less than n minus 1, 1 over n minus 1, then an equilibrium exists. Now, it turns out that the nature of this equilibrium is also a walk-based equilibrium, but unlike what we had before, you have to compute expected complementarities. Okay, so each of these, this is expected complementarity of length 1, walk 1, of length 1, length 2, length 3, and so on. So let me explain one of these. Okay, so suppose I am looking at expected complementarity of length 3. I know this connection exists. Okay, but what I have to do is I have to think about whether this connection exists or not. Okay, so this is given by so, okay, whether J and K are connected, given that I and J are connected. Okay, so this is the probability of their being connected. This is their being connected times the probability that if I is type Ti, J is type Tj. Okay, then because it's a walk of length 3, I'm thinking about the complementarity from that. I need to think about this. So conditional that this exists, what is the expected complementarity here? Okay, so that gives me this type of an expression. So it's the same kind of walk-based result, but I need to take expected complementarities into account. Okay. All right. So what is not true is that the optimal effort is cannot just be conditional on my type. The optimal effort is conditional on everybody's type. The second thing that sometimes people under incomplete information do is they take all possible networks, they compute the Bonasich for every possible network, they average over the Bonasich, and they say that's the Bonasich under incomplete information. Completely wrong, right? Okay. The other thing I want to point out is when we construct network data from asking for friends, those papers assume if I'm connected to you and you're connected to him, I may not know him, but those papers assume that I know your friend. Okay, the indirect walks are assumed. That's not true. I would have to do this kind of an incomplete information belief updating instead of assuming. So all the complete information peer effect type papers, they use this ballista framework, and they implicitly, unless they are using an econometric trick to solve the problem, they are implicitly assuming that the indirect links are known. That's not the case. Okay, now I want to get into the next part, which is I want to show you what difference. So did I answer your question about what difference this type of problem makes to strategic behavior? Okay, so let's think about core periphery networks. And for the sake of an example, nature will only draw core periphery networks, nothing else. Okay, every core periphery network has an equal probability of being drawn. No other network will be drawn. Every other network has zero probability. What's a core periphery network? The core agents are connected to everybody. The periphery agents are only connected to the core agents. So 3, 4, 5 are peripheral agents. They are only connected to the core agents. Okay. So
type uncertainty, action combination, you know your own payoffs, but you kind of uncertain about the other guy's payoffs. So
you can be uncertain about the other guy's strategy also. No? In the Harsani formulation, he transforms the game and
that's it. And you know your own type, you're uncertain about the other types, you're not sure about their pair. You're also not sure about your own pair. Right? Because they're how they're connected internally affects you as well. So that's it.
No. Okay, so what you're saying is, if I was playing a 2-player game, right, I would, I see the payoff matrix, I see my own payoffs in the payoff matrix, right? So on the other hand, if I was playing, and let's see, if I was playing an n-player public goods game, if I'm playing an n-player public goods game, this is not everyone else's.
Not sure about the others.
Yeah, yeah, that's right.
Don't even know your own payoffs. Like until you know the network structure.
You don't need to know the network. So you just form beliefs about everybody else. Right? Yeah, because the payoffs are interdependent, and everything depends on the complementarity term determines the works. Yeah. Uncertainty. I agree. Yeah. So what is so part of the reason why this becomes complicated is if you try to mess with the belief structure even a little bit, it becomes. So we were trying to do intervention on this. It's very difficult to do intervention unless you do ex-ante intervention. Okay, because the belief structure changes as soon as you remove one player. Okay, so you have to do everything ex-ante. Yeah. So another way to think of this result is that in the complete information, the equilibrium action is Bonnet-Sid's centrality of the adjacency matrix. Here, you can think of it as the Bonnet-Sid centrality of the B matrix. That complicated B matrix. If I look for the Bonnet-Sid centrality of the B matrix, because the B matrix, I didn't go into that, but you can write down a weighted graph where the weights are the probabilities that allow for links between different agents. Okay, and then the Bonnet-Sid centrality.
Here, it's a probability distribution for every player on the game that we is playing as well. That's why
on the neighborhood. So you can say on the game. But
right? So it's almost like whether I'm playing this game or this game or this game, because every game is associated with a G.
Yes.
I'm not very sure about what is the G, so therefore I have a probability. Therefore, the game space itself
expands. Yes. Okay, so let's see how this affects. Yeah, go ahead. No, unawareness says you do not know the probability distribution. Okay, you don't. So ambiguity says that I do not know the probability distribution. Unawareness goes even beyond that. Unawareness says that you don't even know if there's a probability distribution, right? So okay, so let's focus on trying to understand what it does to strategic behavior. Okay, so 3 and 4, 1 and 2 are connected to everybody. They're the core. 3, 4, 5 are the periphery. Now let's see what information everybody has. 3, 4, 5 know that they are in the periphery because they are not connected to the other. So take 3. 3 is not connected to 4 and 3 is not connected to 5. So 3 knows that they are in the periphery. The problem is with 1 and 2. 1 and 2 do not know if their friends are in the core or periphery. They are connected to everybody. They cannot see whether these guys are in the core or the periphery. Okay? Now, knowing this, what happens? It causes a difference. So if I look at the information the peripheral agents have, they have the same information as they would in a complete information game. However, they will not take the optimal action associated with the complete information game. Why? They will internalize the fact that the core agents do not know whether they are in the core or the periphery. And since the core agents do not know whether they are in the core or the periphery, they will adjust their action accordingly. Okay? They're the neighbors, yeah. They don't know whether the neighbors are in the core or the periphery. So since the core agents don't have complete information and the peripheral agents are equivalent to having complete information, they will still internalize that fact and not choose the optimal effort level that would coincide with the complete information case. So having said that, it depends on, so we can say a little more. We can actually say it depends on the size of the core. Okay, so the larger the core, the more uncertainty there is, okay, relative to the periphery. So the larger the core, the more uncertainty there is, and the higher is the effort level. Okay, so you overexert effort relative to complete information for a larger core, okay, and underexert for a lower core. This is the relationship that will arise in equilibrium. Okay.
I would say that in the periphery guy doesn't go level, maybe you will not get them.
Yeah. Of course. Yeah, I mean, you can see what happens in an experiment. I mean, we've talked about this. It'd be interesting to see what happens in an experiment, right? And then if you have Tarun there, then what happens in the experiment, right? And so on. Yeah. Okay, so this is the formal setup. So only core periphery networks with equal probability will be drawn. This is the complete information equilibrium effort level. So forget about all this. I explained everything already. This is the incomplete information effort level, not important. So one of the things that we can talk about is typically in the networks literature, you have monotonicity of effort, which is associated with degrees. Okay, so if you have more degrees, generally you will exert more effort. But this is not the case for these types of games. So you can see where there is local complementarity. It actually doesn't matter whether you have complete information or incomplete information. So here you see agent 7 has only 1 degree, but they are connected to a large subcomponent. Here agent 7 has 2 degrees, but they are connected only to this isolated group. So in this case, agent 7 will exert greater effort. So the monotonicity of effort does not carry over in these types of games, whether you have complete or incomplete information. What's interesting is, yes, go ahead. Go ahead. Sorry. Yeah. I think Prita asked this early on, and we said if I relax that assumption, we can tackle that. But that becomes a large game, and it's very complicated. We haven't finished tackling that, is what I would say. Okay. Yeah, but that becomes a very complicated problem. Okay. So you have to look for asymptotic results.
Whether I reveal my network connections.
No. This is the first paper. So the other two things. So we are doing intervention, right? And as I said, we actually have looked at what happens if it's not uncertainty about nodes, but uncertainty about links. The same kind of structure works. We also looked at what happens if you have homophily. We can solve homophily as well. And then, as I said, what happens if there is somebody, the CEO or the village chief, who knows the entire network, and everybody knows, because that matters. What is common knowledge is very important, right? And who is connected, in that case, common knowledge, and who is connected to this person is also very important. Okay. So, however, if you restrict attention to uniform distribution, you get back this effort, because what uniformity does is kind of evens everything out. Okay? So everybody is equally likely, intuitively thinking, uniform distribution will restore this monotonicity in degrees. Every network is equally likely. Okay, so I just make uniform distribution instead of arbitrary distributions. So if I allow for uniform distribution, then this result that we had, that this monotonicity result, you can recover the monotonicity result. Okay. The other thing is, under uniform distribution, everything depends on the degree. Okay, so what we're saying is, if you assume uniform distribution, unlike the Galliotti et al. Paper where they require anonymity, you generate anonymity in equilibrium, because I don't now need to know the identity of the agent anymore. I just need to know the degrees. Okay, so uniform distribution gives me anonymity of agents. The only thing that matters is degree. All right.
Had value of lambda is 0.1, but wouldn't it be less than 1 upon independence?
That's the largest. I mean, that's a sufficient condition.
So if n is k or not, so it should be less than 1 upon. I mean, if it's satisfying or
Yeah. It is satisfying. Yeah.
like a boundary.
No, it should work. No, there are 10 agents. Okay.
It's there.
Yeah.
So it's almost like the
1 over n minus. Yeah, I mean, this is just an illustrative example. You can play with this. You can create.
like the secondary will explode.
Yeah. I mean, we're also not very happy with this example because this is using components. So ideally, the example should not be using 2 components. But you just have to show some. Yeah, it holds. I mean, I think the main point behind introducing this was to say that monotonicity does not work, but if you introduce uniform distribution, you can get back to monotonicity. Okay, that's the key point here. All right, so the equilibrium actions are again walk-based. It's not expectations of a complete information outcome. So we saw that. In fact, it depends on the type of every agent in the network. And the BNE is robust to different types of information structures. Okay. All right. That was a lot of information very quickly, but I hope I was able to get some of it across to you all. So we have time for a few questions, no?
Network structure and how overexerted, or so you gave that result for stars. Is that generalizable? Stars may core periphery. So is that generalizable to say that if you have some structures, certain type of structures lead to overexertion? So what happens to trees? What happens to cycles?
So it's a good question. In general, it is very hard to say something unless you tell me something more about the nature of the parameters and the uncertainty, right? So let me see, in a tree, what is happening? So in a tree, it will depend on the length of the tree. It will become, the logic will be very similar to the core periphery, right? So the longer the tree, the more uncertainty there will be, and therefore, so agents in the center of the tree will have a lot of uncertainty. Agents in the periphery will also have a lot of uncertainty.
Where in the tree already?
Yes and no, because the end agents are only connected to one person, right? Whereas and the middle agents have to have beliefs over half the network on either side, but the end agents have to form beliefs over a much longer chain of network, right? So it's going to depend on the amount of walks on which you have to form beliefs. Okay, so it's going to always depend on the ratio of the people with uncertainty versus the people with uncertainty, and the number of extended walks that you have to compute.
So uncertainty is growing with the network size, which is n. But there are no results to say.
Well, no, actually not. So if I have a large network, but the core is only 2 agents, right? So a large part of the network knows exactly what's going on. Only 2 people don't know what's there.
Got it.
So it depends on the size. So that's why that result also depends on n as well as what proportion of n is core. Okay.
So first word with like information.
Well, the other stuff is with degree distributions. Degree distributions cannot do this core periphery type. They cannot show how effort level will change because you just know degrees. You can't really play the game.
Says how many people this person is connected to, not
How many?
Yeah, identity is not important. Identity is not there. Not. In fact, they need the assumption that you don't know the identity. Yeah. So yeah. So studying strategic interaction is kind of difficult.
that the same integrity can have multiple graphs.
That's right.
So it's not only that, therefore,
How will you?
the core
No.
values are connected to everyone.
No.
Whether the others are like,
No. One second. Okay. So nature draws core periphery only. Okay. Only core periphery. This is an illustrative example, right? So I restrict attention to core periphery graphs. So uniform on core periphery. Now, once this network is drawn, okay, agents 3, 4, and 5 know that they are in the periphery. Why? Because they're not connected to everybody. So by definition, they are in the periphery because the definition of a periphery agent is that they're not connected to everybody. The definition of a core agent is they are connected to everybody.
they don't have complete information. Periphery also do not have complete information. Because if there are
No, periphery has complete information. Why not?
suppose one of them, right? So that depending on connection of, for example, here you have
So peripheral agents know that they are connected to, they're not connected to. So 3 knows that they're not connected to 4 and 5. That means 3 knows that 4 and 5 are periphery agents. Okay. And 3 is connected to 1 and 2. So 3 knows that 1 and 2 are core agents. The definition of core periphery, not assumption. That's not an assumption, that's a definition. The difference between assumption and definition, right?
So let's try outside. So thank you everyone for coming and thank you for your time. And we'll go outside and have chai now.
Thank you.
with